Here's the comments or helpful hints for the final selection of problems, just a couple of problems having to do with power in Chapter 6. First problem, we've got an elevator with mass given, starts from rest, it moves upward for a certain amount of time with constant acceleration until it reaches a cruising speed of 1.8 meters per second. Find the average power delivered by the elevator motor during this period. So in this case, and we should pay attention, it says if you calculate the answer in watts, you have to convert to kilowatts by dividing by 1,000 if you've got it in watts. So in this case, we know the final cruising speed of the of the elevator, and so we can calculate using the definition of average power. The power is the work done by the elevator motor during this period. In other words, we can think of the work done by, if you imagine a simple vision of an elevator as a rope holding a box, right? And it's the rope's pulling it up. It's the work done by that rope force. We got to figure out what the rope force is in this case if we're going to calculate the work done by it. And that's the reason we're given this final speed. We know we can use that to figure out what its acceleration is. The acceleration is equal to the change in the velocity divided by the change in time. So its change in velocity is 1.8. The change in time is 4 seconds. You divide those two, you'll get the acceleration. Then I can do, say, take plus y equal, it is in the upward direction. F net y equals may, and in this case, ay is not 0. So free body diagram for the elevator, it's got a weight force going down and the tension force going up, and they don't balance because it's accelerating upward. So the tension force minus the weight force, 766 times 9.8, is equal to the mass of the elevator, 766, times the acceleration that we calculated, and from that we can calculate what the tension in the rope is that's holding the elevator. That's the same as the power output by the elevator motor. Okay, I'm sorry, same as the force output by the elevator motor. And in this case, once we've got that force, then we can figure out that we need to figure out over what distance this thing is moving. And in this case, we know its acceleration, and we know the amount of time it's accelerating for that at that rate for, so we can use some kinematics to figure out how far it moves in those 4 seconds. Once we've got that, we can do the elevator kind of cable force times the distance it moves is the work done by the elevator, and the average power is the work done by the elevator, say cable force, divided by the time it took, which is 4 seconds. And that would give you an answer in watts. Then we divide by 1,000 to get it in kilowatts. Second problem, a skier of mass 74.6 kilograms is pulled up a slope by a motor-driven cable. How much work is required to pull him up 63.7 on a certain inclined plane slope? And again, in this case, answer in kilojoules. So we'll first calculate it in joules. So I've got to figure out what the rope force is that's pulling, and we're pulled at a constant speed. So in this case, I could use that constant speed to get the instantaneous power, but in this case, we could just say, look, if we're being pulled at constant speed, the acceleration is 0, and therefore the rope force and the component of the gravitational force along the inclined plane direction have to balance out. So I would, if I take x to be along the inclined plane, take F net x to be equal to 0. That's going to be the rope force minus that parallel to the plane component of the weight force. That will allow me to calculate what the rope force is, and then if I want to know how much work is being done, we just multiply the rope force by 63.7 meters, and that would give me the work done by the rope force. in joules, and then of course I'm going to divide by 1,000 to get it in kilojoules. What power must a motor have to perform this task? Answer in units of horsepower. So we'll first figure it out in SI units for power, which is watts. And so what we would do for that is just say, well, we know the speed the person's going at, and we've just calculated the rope force, so we can use our instantaneous power formula, which is the instantaneous power is Fx times Vx if the thing is moving along the x direction. So we just found our rope force, that would be our Fx, and the Vx would be 3.2 meters per second in my version of the problem. That would give me the power in watts, and then you've got to look up what 1 horsepower is and change units from watts to horsepower. You can look that up, I'm assuming, in the inside cover of the book, or just Google it to make that conversion to horsepower. That's what the HP is. All right, good luck on that.